Welcome. Today we're diving into a hidden world, a world of absolutely immense power. We're talking about the giant motors that are, quite literally, the heartbeats of our modern world, powering everything from massive factories to colossal ships. So let's jump right in.
So, have you ever stopped to think about this? I mean, how do these gigantic machines, under unbelievable stress, just keep on running for years and years without just grinding themselves into a molten heap of metal? What's the secret sauce?
Well, the answer comes down to a constant, brutal battle against two invisible enemies. Friction, which wants to wear everything down, and its destructive partner in crime, heat. And the weapon in this fight is lubrication. But, this is way more sophisticated than just squirting a little oil on a squeaky hinge.
So here's how we're going to break it all down. First, we'll look at the problem itself, friction and heat. Then we'll explore two totally different solutions, the cleverness of self-lubrication and the brute force of, forced lubrication. And we'll wrap it all up with a head-to-head showdown to see which one you choose and why.
You see, when it comes to motor lubrication, you've basically got two different schools of thought, a real fork in the road. You can either design a system that cleverly uses the machine's own motion to lubricate itself, or you can bring in the big guns and use external power to force that oil exactly where it needs to go.
And here's the key difference. Self-lubrication is kind of passive, right? It's brilliantly self-sufficient. It just uses the motor's own spin to do all the work. On the other hand, forced lubrication is totally active and super powerful, using pumps to create this controlled, pressurized flow of oil. Let's start with that first, more elegant path.
Okay, first up, self-lubrication. You could argue this is the more elegant approach of the two. It is all about designing a system that just brilliantly uses the motor's own energy to solve its own problems. It's pretty clever.
So the core idea here is what we call a self-acting system. A great way to picture it is to think of an automatic water wheel, but for oil. The motor's own spinning shaft becomes the engine of its own lubrication. It just scoops up oil from a little pool and delivers it right where it's needed. No pumps, no extra power, nothing.
And there are a couple of classic ways to do this. The first is the oil ring. It's just a simple metal ring hanging on the spinning shaft. As the shaft turns, the ring dips into an oil bath below and carries this continuous film of lubricant up to the top of the bearing. Simple, right? Then you've got splash lubrication, which is, it's exactly as messy and effective as it sounds. The moving parts just literally splash oil everywhere inside the casing, coating everything. So the real takeaway here is that their simplicity is their strength. Because there are no external pumps or complex gadgets, there are way fewer things that can break. And that makes them incredibly reliable for a huge range of motors that are running under pretty normal speeds and loads. But what happens when things get extreme?
And that's when we enter the world of forced lubrication. This is the heavy-duty, high-performance solution. This is what you bring in when the motor's own motion just can't cut it anymore.
So why would you need all this extra power? Well, it comes down to three things: speed, load, and temperature. When a motor is running incredibly fast, carrying a massive load, or getting crazy hot, lubrication stops being just about reducing friction. It becomes about actively removing heat. And for that, you need a powerful, active system to pull that heat away.
The most common setup here is a circulating oil system. And honestly, the best way to think about it is like a circulatory system for the machine. You've got a heart, that's the external pump, pressurizing the oil. Then that oil flows through kidneys, the filters, to clean out any gunk. From there, it goes through a radiator or a cooler to get rid of all that heat before it gets pumped, clean and cool, right back to the bearing. It's a continuous, life-sustaining loop.
And for the most extreme jobs, engineers get even more creative. You have oil mist systems, which use compressed air to create a fine fog of oil. This mist cools and lubricates, but it also creates positive pressure that actually pushes dirt and dust out of the bearing. And then there's jet lubrication, which is basically a power washer for heat, just blasting oil directly onto parts to cool them down under insane loads.
So this forced lubrication toolkit is some serious business. You've got the heart, the radiator, the kidneys, all often packaged together into one single control center, which they call a lubrication skid. It's not just a few parts. It's a complete external life support system dedicated to keeping that motor alive.
All right, so we've seen the two big philosophies, the elegant, self-sufficient systems and the powerful, heavy-duty ones. So now it's time for the showdown. How on earth do you choose?
When you lay it all out like this, a really clear pattern starts to emerge, doesn't it?
The self-lubricating methods, they're all about simplicity and reliability. They're perfect for your average everyday applications. But the second you look at the forced systems, the keywords change. Now we're talking about active cooling, filtration, positive pressure. These are all features designed to handle extreme loads, insane speeds, and intense temperatures. The choice always comes down to the demands of the job.
So here's the simple rule of thumb to walk away with. The moment you introduce any of those extremes, blistering speed, crushing loads, or intense heat, the balance just tips. The elegance of simplicity has to give way to the raw necessity of power and control, and that is when a forced lubrication system becomes absolutely essential.
And at the end of the day, that's really what this is all about. Picking the right lubrication method, that's the invisible engineering, the unsung hero that allows the massive machines that power our world to just run reliably day in and day out without us even thinking about it.
And that kind of leaves us with one last thought. We've just pulled back the curtain on one huge, invisible system that our entire world depends on. It really makes you wonder, what other hidden engineering marvels are out there, quietly keeping everything going?